All right, hi everyone. Welcome back to section 4.1. And in this 4.1 video, we're gonna take a look briefly over linear independence and linear dependence because linear independent solutions are key to building up our general solution and our basic idea of how solutions are formed. So, we are gonna either review linear independence and dependence, whether you've taken linear algebra or not, or if you haven't, we're just gonna briefly go over it to help us get to that general solution for homogeneous, non-homogeneous phase. This is a building block. We need linear independent solutions. So let's go ahead and get into the definition. So what is linear dependent? So if we have a bunch of functions together, like f1, f2, all the way up to how many functions you have, they're said to be linear dependent functions if there exist constants, c1, c2, all up to cn, that aren't all zero, like they could be one, two, three, you know, one, two, three, -5, etc. Bunch of constants that the linear combination of these functions with their constants equals zero. So the constants are not zero, but if we add up all of the functions as a linear combination, we get zero. And so the opposite is the case for linearly independent functions, where the only way we'll get zero if we add up our linear combination is if all of our constants are zero. So all constants are zero. And so we want linear independence. Okay, that's what we want. That's what we, only way we could build up our solutions to these differential equations. So we're going to need these linearly independent solutions and sets, but what I want us to do is kind of work our way through with the definitions before we get going on uh, this building block. So let's kind of go over what a linearly dependent set would look like. So dependent. So here's example 6, linear dependent set of functions. So consider these set of functions. We have f1 equals cosine squared, f2 equals sine squared, f3 equals secant squared, f4 equals tangent squared. And we already know that these are linearly dependent functions because their linear combination, C1, C2, C3, C4, it all equals zero, their linear combination for non-zero constants. So let's see what these possible constants could be. So let's consider constants, C1 equals 1, C2 equals 1, C3 equals -1, and C4 equals 1. And these are all non-zero constants. Okay, so let's see what that linear combination would look like. I'm just going to plug these into the equation up top, and we're going to see y equals 0. So we'll get uh, 1 cosine squared x. So I'm just going to write cosine squared x plus sine squared x minus secant squared x because of that -1, and then plus tangent squared x, or let me not write 0 yet. Okay, well, how does this equal 0? So if you could recall a couple trig identities, that cosine squared plus sine squared equals 1, and that tangent squared minus secant squared also equals 1. So this ends up being 1 minus 1, which just equals 0. So this is linearly dependent. Okay, we're getting a 0 for non, the linear combination becomes 0 with non-zero constants. That makes us linearly dependent. Okay, so for linear algebra, there's definitely more of a deep dive into linear independence and dependence, but we're just kind of going over the basics and the definitions. So we want linear independent sets. So let's sort of change our focus to how we determine if a set of functions is linearly independent because that's what we want. So linear independence. So like I was saying, we are mainly focused on linear independent functions. And that means we are focused on linearly independent solutions to a differential equation. This is another building block. So there's a nice test to see if functions are linearly independent or dependent. And what that's called is the Wronskian. And what the Wronskian does is use a determinant to compute the Wronskian for this test. Okay, so how does a Wronskian work? Let's look at this arbitrarily. So consider two functions, y1 and y2, and it's saying compute the Wronskian. So the way we would do this is we would write, W for Wronskian, and you would typically write the functions, parentheses, y1 comma y2. You'd write the functions that you're given, that you're trying to determine if they are linearly independent or not. And so it's a determinant if you've seen this before. Uh, you would write y1, y2, and in the first row. And then in the second row is their derivative. So this would be like y1 prime. Let me write 1 like that. And so this would be y2 prime. And then what you would do is you would just cross multiply. So y1 times y2 prime, and then y2 minus y1 prime. And so don't forget, keep in mind that you need to subtract them. It's a determinant. So y1, y2 prime minus y1 prime times y2. And so this would give us some answer. Okay, so how do we determine whether something's linearly independent or dependent? So here's the key. If the Wronskian equals 0, then y1 and y2 are linearly dependent. Okay, so it's the same idea where if we have non-zero constants in the linear combination, we get 0, it's linearly dependent. Okay, and if the Wronskian doesn't equal 0, well, then y1 and y2 are linearly independent. Okay, so the Wronskian exactly tells us whether solutions are linearly dependent or independent. Okay, so let's try out an example now. So example 7, linearly independent or dependent. So use a Wronskian to determine whether y1 equals cosine x and y2 equals sine x are linearly independent or linearly dependent. So let's go ahead and try this out. So we have Wronskian, we want to write cosine x. sine x. Looks like our y1, y2. And so we set up the determinant. This would be cosine x, sine x. And so the derivative of cosine is negative sine. Derivative of sine is positive cosine. And so we cross multiply now. And so we get cosine x times cosine x minus sine x times negative sine x. So this is cosine squared x plus sine squared x. But cosine and sine squared, well, that's a nice identity that we previously saw. That's 1. And 1 does not equal 0. So therefore, y1 equals cosine x and y2 equals sine x are linearly independent. Okay, so let's go ahead and move on to example 6, or excuse me, example 8. So a similar question. We have two functions here, y1 and y2. We want to see if they're linearly independent or dependent. Note it's not asking us to set, it's not saying use a Wronskian. This is our intuition. So it doesn't completely say it, but what we want to do here is use a Wronskian. Okay, so what I want you to do is pause the video, use a Wronskian, try this problem out, and see if it's linearly independent or dependent. Okay, welcome back. So hopefully you tried this problem out using the Wronskian. So let's kind of go through this step by step. So our first solution was e to the x over 2. And then our second solution was x e to the x over 2. And just pay attention, we have to use a product rule here. So when we take the derivative, it would be this 1 half x e to the x over 2 plus e to the x over 2. And we also have a chain rule to deal with that e to the x over 2. It would just be 1 half times e to the x over 2. So just be careful with your derivative rules. And then, we cross multiply using the determinant. And so what we end up with after we cross multiply is 1 half x e to the x plus e to the x minus 1 half x e to the x. So the 1 half x e to the x cancel out. And so what I'm left with is just, excuse me, is just e to the x. Well, that's strange. It's not a number. On the last example, we got the number 1. We can obviously come to the realization that it's not equal to 0. But the great thing about exponentials is that we know they never equal 0. So we know for a fact that e to the x would never be 0. So we can say not equal to 0. So that means that these two functions are linearly dependent. And just make note that e to the x is never 0. So therefore, y1 equals e to the x over 2 and y2 equals x e to the x over 2 are linearly independent. Okay, so just to recap, we discussed what linear independence and linear dependence are. We know that we want linearly independent sets, that those are key to our solution building. And we use a Wronskian to make sure we have linearly independent sets. Okay, so that's the main goal. And in this video, we were just focusing on linear independence dependence, which is another building block to our eventual general solutions to homogeneous and non-homogeneous DEs. But that's it for this video. Just wanted to focus on linear independence. And so I'll see you in the next one and take care.